Stability is an important requirement for safe operation of floating and submerged bodies, and it ensures the safety of floating bodies against the external forces. Stability is a characteristic or ability of the body which causes it to return to its original position of equilibrium after having been disturbed through a small displacement from its equilibrium position. A body is said to be in equilibrium when there is no resultant force or moment acting on it. There are three states of equilibrium. A body is in stable equilibrium if after having been disturbed from its original position, it tends to regain its original equilibrium position. However, the same cone is in unstable equilibrium if placed on pointed end, as it will never come back to its original position. And it is in neutral equilibrium when it neither returns to its original position nor does it increase its displacement. It will simply adopt its new position. Stability is thus one of the important criteria in design of enduring structures, whether used on land, in water, or in air. Whenever a body is immersed in air or water or in any other fluid at a certain depth, the fluid exerts pressure at all the points of its surface. However, the intensity of pressure varies directly, with depth below the free surface being minimum at top and maximum at the bottom. The resultant of all these fluid pressure forces is always directed in a direction opposite to that of gravity and causes apparent loss of weight of the body. This phenomenon of apparent loss of weight of the body in fluid was first discovered by well-known Greek scientist Archimedes in 2nd century BC. Archimedes was one of those to study at Alexandria under the disciples of Euclid, and eventually he personified to an extreme degree the analytical and practical attainments of the period. Born at Syracuse, Sicily, the son of an astronomer, he grew up to become a renowned scientist and mathematician. Not only he discovered method of measuring area of closed curve, but also invented many machines to destroy the ships of the attacking enemies. He claimed that given a lengthy lever and a place to rest it, he could even lift the earth. The most popular of the legends about Archimedes is the one about his discovery of the principle of buoyancy. Hiero, first king of Syracuse, believed that he had been cheated by his goldsmith in making his crown. He asked Archimedes to check the purity of gold used while keeping the crown intact. For days he was perplexed by this difficult problem. The solution is said to have occurred to him one day as he entered the pool of a public bath, whereupon he elatedly left for home without pausing to dress, shouting as he ran, "Eureka!" meaning thereby, "I have found it." He took solids of gold and silver, each one having weight equal to the weight of the crown. Then he immersed these three objects one by one in water and found that water displaced by each one of them was different, meaning thereby that the crown was not made of pure gold. From this he concluded that a body immersed in a fluid is buoyed or lifted up by a force equal to the weight of the fluid displaced by it. This principle is known as Archimedes' Principle. To further understand this principle, we have a metallic cube and plastic container. the volume of metallic cube is equal to the inner volume of plastic container from bottom to the line marked red on the container. Both plastic container and the metallic cube are suspended from the spring balance and weight. We find that there is decrease in weight of the assembly when the metallic cube is fully immersed in water. This is due to the force with which the metallic cube is lifted up. Let us put water in the plastic container till the needle of the spring balance is restored back to its original position. We find that weight of water added to balance the upward force is just equal to the weight of the volume of water displaced by the metallic cube. This upward force with which the metallic cube is buoyed up is called buoyant force, and it acts vertically upward through the center of gravity of the volume of water displaced by the metallic cube. The point of application of buoyant force is called center of buoyancy. The magnitude of the buoyant force depends upon the volume of the immersed object and not of what it is made of. A body will float in fluids if the buoyant force is equal to the weight of the body. But will sink if the weight of immersed body is greater than the buoyant force. The stability of submerged bodies depends upon the location of center of gravity G with respect to center of buoyancy B. A submerged body is in stable equilibrium if the center of gravity lies below the center of buoyancy. As such, any disturbance due to some external force produces a restoring couple which establishes its original position of equilibrium. If the center of gravity is above center of buoyancy, the submerged body will be in unstable equilibrium. A small deflection from vertical results in unbalanced couple, tilting the body further away. A submerged body is in neutral equilibrium if buoyant force and weight always remain in line. However, for floating bodies, such as a ship floating in still water, there are two forces acting upon it. Its weight acting downward through the center of gravity and buoyant force acting upward through the center of buoyancy. In the upright position, the centers of gravity and buoyancy are on the same vertical line. As the ship is made to heel over at an angle by some external force, the center of gravity G of the ship will remain in the same position, but the center of buoyancy B will move outward to a new position B1 in the direction of the heel. A vertical line drawn through the new center of buoyancy intersects the original vertical line of the ship at a point known as the metacenter M. The two vertical forces now acting on the ship are no longer along the same vertical line and form a couple, which can either bring the vessel back to its upright position or push it further over. So long as the center of gravity remains below the metacenter, the couple will always do the vital job of returning the ship to the upright position. Otherwise, it will increase the original heel of the ship, which may lead to overturning. The natural ability of the vessel to resist the external forces and return automatically to the upright position is known as its stability. The necessary and sufficient condition for the stability of a floating vessel is that the point M, the metacenter, should be above the location of G, the center of gravity of vessel. Distance GM is called metacentric height, which is positive for a stable vessel. Let us experimentally determine the value of GM, the metacentric height of the given vessel. We have sheet metal pontoon carrying a single mast, a plumb bob to read the angle of tilt on the scale, an adjustable weight to change the center of gravity of pontoon, and a jockey weight which slides along a bar parallel to the base fixed on the pontoon. It is given that weight of pontoon is equal to 2.6 kg, weight of jockey weight is equal to 200 grams. The height of the center of gravity of the pontoon above its base is established by keeping the adjustable weight in one known position and balancing the pontoon on a horizontal bar. The pontoon is allowed to float in water, the angle of tilt being 0 for central position of the jockey weight. Angles of tilt are recorded by moving the jockey weight by small distances to one side and then to the other side. Another set of reading can be recorded by changing the position of adjustable weight, thereby changing the position of center of gravity of the pontoon. The metacentric height is obtained by using the formula Gm is equal to small w over capital W into dx over d theta, where small w is weight of jockey weight, capital W is weight of pontoon. dx is horizontal shift of jockey weight, and d theta is angle of tilt of pontoon. From the experimental results obtained, we find that as the height of center of gravity of the pontoon above water surface decreases, the metacentric height, gm, increases, leading to increased stability. However, height of metacenter above water surface remains fairly constant. Thus, stability analysis of floating bodies, such as boats, cargo ships, floating docks, etc., depend upon the relative position of center of gravity and center of buoyancy with respect to metacenter. Thus, we find that the natural ability of the floating and submerged body to resist the external forces and return automatically to the upright position is known as its stability. A body in equilibrium may be unstable, or neutral equilibrium. A body immersed in air or water is subjected to a resultant upward force causing the apparent loss of weight, a phenomenon first discovered by well-known Greek scientist Archimedes. He said that a body immersed in a fluid is buoyed or lifted up by a force equal to the weight of the fluid displaced by it, known as Archimedes Principle. The upward force with which a body is buoyed up is called buoyant force, and its point of application is called the center of buoyancy. The body will float in fluids if the buoyant force is equal to the weight of the body. It is the relative position of centers of gravity and buoyancy which determine whether a submerged body is in stable, unstable, or neutral equilibrium. However, for a floating vessel to be stable, the necessary condition is that the point M, the metacenter, should be above G, that is, distance mg should be always positive. Moreover, the stability of the pontoon decreases as the height of center of gravity of the pontoon above the water surface increases, and vice versa. Although many concepts go into the design and stability analysis of floating and submerged bodies, but all this would not have been possible without the invaluable contribution of Archimedes. Why does a balloon stop rising further after attaining a certain height? If you are sailing a boat and the boat tilts to your right side, to which side the center of buoyancy will shift? Why is it that a man with inflated life-saving belt around his waist does not sink? Does a body experience the same loss of weight in two given liquids of different density? Which pontoon is more stable, one having center of gravity near its bottom or the other having center of gravity near its top?